Hi everyone, today's lesson is on Unit 2.2, Evaluating and Graphing Polynomial Functions. And the first part of your notes says graph the function using a graphing calculator. So you can also use Google. If you don't have your calculator at home, you could just type in the function into the Google search bar and ask it to graph, and it'll give you a good sense of what those functions are. Just double check those in your notes. I know you started doing those in class with your calculator. And remember to phrase your end behavior as x approaches positive infinity and as x approaches negative infinity. So again, when we're looking at a graph, x to the positive infinity is off to the right, x going towards negative infinity is off to the left, y for positive infinity is vertical up, and negative is down. Looking at the vocabulary, we're going to start with a polynomial. A polynomial function is actually a monomial, which is just a function with 1 as its largest power, or a sum of monomials. So again, you're really looking for a function that has an exponent that is greater than or equal to 2. So all year so far we've been studying quadratics. All quadratics are polynomials. The leading coefficient of a polynomial is the constant term that is in front of the variable with the highest exponent in that equation. So we usually say it's the first term if it's in standard form. The degree, again, is the power, and it's the highest power in that equation. The constant term is a when there's no variable attached, right? So it's not a coefficient, it's just a whole number. And standard form, again, is x to the n plus x to the n minus 1, and so on and so forth until you get a x to the n, and then x to the 1, and just a to the 0. So we're consistently decreasing the value in our exponents. When we're talking about polynomials, there's certain types. This depends on the highest value of the power or the exponents. So when I have a degree of 0 in my polynomial, I'm just looking at a constant. I'm looking at a whole number, something along the lines of f of x is equal to 14. When I have a degree of 1, I'm looking at a linear function, right? We see that in our linear equations like y equals mx plus b, or as an example, f of x is equal to 5x minus 7. So there's no visible power, which means that it's just a degree of 1. Quadratics, again, what we've been working on all year, have a degree of 2. And an example of that would be f of x is equal to 2x squared plus x minus 9. The third degree is going to give us a cubic function. So what that means is we're going to have an f of x is equal to something to the third power, like x to the third, and then minus x squared plus 3x. And again, we can have a constant there as well. And lastly, a function with a degree of 4 is a quartic function. And that means that its highest power is going to be to the 4th. So an example, x to the 4th plus 2x minus 1. Example 1 says decide whether the function is a polynomial function, and if so, write it in standard form and state its degree type, and leading coefficient. So when I look at a, I know that there is the highest power is to the 4th, so this is going to be a quartic equation. There's no negative powers, which is important. So I'm saying, yes, it is a polynomial function. It's quartic. So it has a degree of 4. And the leading coefficient is actually 1 because there's no whole number in front of that x to the 4th. So we assume that it's an identity, which is just 1. For letter B, again, yes, it is a polynomial. In this case, it's going to be a quadratic because my highest degree is 2. And the leading coefficient on this is actually pi, right? The pi is in front of the variable with the highest coefficient, with the highest exponent, excuse me. Looking at end behavior for polynomials, we want to make sure that we get our graphs in to this little diagram first. So I'm just going to take a second and draw how each of these functions appears ahead of time. And you can check these on a calculator if you wanted to. When you have a leading coefficient that's positive and the degree is odd, when you have a leading coefficient that's negative and the degree is odd, or vice versa when the degrees are even. These are very similar to the examples we did on the very first slide. So looking at a leading coefficient that's positive with an odd degree, so what that means is something like x to the third power, we're going to get a function where as the function approaches infinity, the function approaches infinity as x approaches infinity. And the function approaches negative infinity as x approaches negative infinity. And you could, again, look right at the graphs and make these assumptions. So anytime you're asked a question like this on an exam, feel free to use your calculator if you do not have these facts memorized. But these are standard assumptions. So below, a positive coefficient with an even degree is going to give us a function that approaches infinity as x approaches infinity, and a function that approaches infinity as x approaches negative infinity. A leading coefficient that's negative with a odd degree as the function approaches negative infinity, x is approaching negative infinity. And vice versa as the function approaches infinity as x approaches negative infinity. And then lastly, we have a graph with a leading coefficient that's negative but has an even degree. And that shows us that the function approaches negative infinity as x approaches infinity. And the function approaches negative infinity as x approaches negative infinity. And as I mentioned, these are all standard forms. So anytime you're looking at a polynomial, check the coefficient, whether it's positive or negative, and check the degree, or the highest power, right? Whether it's odd or even. And that should give you a standard form for how those graphs are going to look. Example 2 says to use direct substitution to evaluate. This is just a straightforward polynomial function. And it says when x is equal to 3, what is my solution going to be? So I'm just going to plug in 3 for all of my x values. So 2 times 3 to the 4th minus 5 times 3 to the 3rd minus 4 times 3 plus 8. And because of my order of operations, I have to solve for my exponents first. So I'm doing 3 times 3 times 3 times 3, 3 times 3 times 3, and I'm getting those solutions to plug into my equation. So 2 times 81 minus 5 times 27 minus 4 times 3 plus 8. And then again, do my multiplication, just continue simplifying. That's going to give me 162 minus 135 minus 12 plus 8. Which all comes out to 23. So it's just that simple. It's really just substituting to evaluate that expression. Lastly, example 3 asks me to graph the polynomial function. The way I'm going to do this is I'm going to look at that function and I'm going to decide some values to plug in for x, and then I'm going to solve for y. So as I'm looking at this, if I plugged in the value -3 for x, I would get 24 for y. -2 for x is 3 for y. -1 for x is -4 for y, and so on. And I'm just doing that by taking the x value, plugging it into that equation just like we did in example 2, and solving for the y value. And this is giving me a set of coordinate points that I can then use to graph the function. So once I have a good number of points here that are fairly symmetric, right? I started at -3 and I went to -2, -1, 0, 1, 2. Then I can plot several of those points and take a look at how this function is actually going to look. Now I can check and see that my leading coefficient is negative and that my power, or my degree, is an odd number. So I know that the trend of that graph is correct. Go ahead and do part B independently. We'll take a look at those graphs next class.